Welcome to everyone. So the next topic in the mechanics unit is conservation of angular momentum. So now we have to prove whether the angular momentum is conserved before action and after action. So here in angular momentum, we are going to concentrate the what is that moment of inertia and what happens to the angular velocity when there is no torque. So now we know the relation between torque and angular momentum. That is, tau is rate of change of angular momentum. It's nothing but Newton's second law of motion. That is, Newton's second law of motion for the rotational bodies. That is, torque tau is equal to dl by dt. If there is no external torque is acting on the body, then we can say tau net. Net torque is equal to 0. Then the angular momentum L, that is will be a constant. That is, if tau net is equal to 0, dl by dt is equal to 0. Therefore, L is a constant. So here I have given in some other video what happens to the moment of inertia and angular velocity. They are interrelated. And also the I is inversely proportional to omega. If I increases, omega decreases. So we can prove this. So this tau net is equal to 0, dl by dt is equal to 0. Then L is a constant. This is called as a law of conservation of angular momentum. It shows that the angular momentum of the rigid body is constant at any instant of time t if the net torque is 0. Now, in other words, we can say the net torque is 0, then the angular momentum of a rigid body will be equal. Let L1, L2 are the angular momentum, then we can write L1 is equal to L2. We know another one formula for the angular momentum, that is L is equal to I omega. For L1, it is I1 omega 1, and L2, it is I2 omega 2. Already we know L is a constant, and if there is no net torque is acting on the body, then L will be a constant. Therefore, I omega also tends to be 0. If I omega is a constant, then we can write it in a proportionality term. That is, I is directly proportional to 1 by omega. That is, I and omega are inversely proportional to each other. That is, therefore, for a rigid body, when the momentum of inertia increases, then the angular velocity decreases and vice versa. See the figure. In a rolling chair, the man is sitting and rolling. So he will do two actions. Once he have to stretch his hand and rolling, and his hand is closer and is rolling. So see the speed of the wheelchair. When his hands are stretched away, his spinning is slow. When hands are closer to that man, then the spinning is increases. Because the reason is when the hands are stretched away, the moment of inertia decreases, angular velocity increases, the spinning will be decreases. When the hands are stretched towards the body, the moment of inertia decreases, angular velocity increases, the spinning is increases. So clearly here the illustration is explained. Let us consider one striking example of an ice dancer in figure A and figure B. In figure A, the dancer spins slowly because her stance are stretched out because the moment of inertia is large, omega is small. In the second figure, the dancer spins faster because the hands are brought close to the body. Here, the moment of inertia decreases, angular velocity increases, spinning also increases. So I think you have understand. Thank you.